Hello, this is Jake White, and this is my Physics 2212 Lab 3. We will be investigating magnetic dipole. In this lab, we're going to measure and analyze the magnetic field of a bar magnet. We want to measure the strength of the magnet at different locations and then compare the values to theoretical values from the PHYS law. Using measured values, I will create a computational model using GlowScript to model the fields and interactions of the bar magnet system. So on the right, you can see our experimental results. So from the experimental data, I calculated the distance dependence to be negative 2.9272 meters and the value of the magnetic moment to be 2.696 ampere meters squared. At the bottom, you can see the presentation structure. So here's the fundamental physics. So first the Biot-Savart law, and then the distance dependence, and then magnetic field of a dipole, and lastly superposition. So the materials that we'll use in this lab is tape, ruler, flat surface, bar magnet, and a magnetometer. So here's the procedure. So for setting up the magnetometer, first you remove electrical equipment and steel objects from the area around the magnet, and then rotate the phone so that it reads BX is 0 and align ruler with the bottom edge of the phone. Then orienting the phone vertically and place magnet near the phone to find the location where BX is minimized. Place the tape on the phone in this location, and then orient the phone horizontally and place the magnet near the phone and find the location where BY is minimized, and place the tape on the phone in this location. And the magnetometer is located where the upper part of these two tapes intersect. So then to get data for the first part of the experiment, find a distance from the magnet to the distance that produces a magnetic field of the next component of magnitude 20 micro, and then repeat this for these other values and then record these distances in the spreadsheet. And then here is the procedure for the off-axis field. I won't read it, but you can look at it. And then here's our spreadsheet data. So on the top left, you can see the different trials for the distances calculated at certain magnetic strengths. So you can see that there's 3 trials for each R, and then we average those out to get the average R from those trials. And then averaging the magnetic strength as well, which that's all constant, and then doing that and then taking the natural log of both, we get this graph on the right, which is very useful for calculating values later that you'll see. And then at the bottom, you can see values for the off-axis field calculations. You can see D perp, where it was measured 3 different times to get the average, along with the X, Y, and Z components of the magnetic field. And then, of course, the Y component of the magnetic field had to be corrected if you looked in the procedure for the off-axis field. So here's the calculations. So the distance dependence n can be found using this equation. And from the equation of the graph, we get that n equals negative 2.9272 meters. And then we can solve for the magnetic moment using that equation, where k equals e to the negative 14.433. And from this equation, we get that the magnetic moment equals 2.696 ampere meters squared. So here's the GlowScript code. So on the left, you can see where the magnet is initialized and the magnetic moment is plugged in. And then at the bottom, you can see where the Biot-Savart law is used to create that function. And then on the right, you can see where the axes are created, essentially. Yep. And then here on the left, again, you can see where the perpendicular vectors are created. And then on the right, you can see where the average D perp is added in. And then from that, the distance D is calculated. And then we get the 45-degree vectors as well. So here's the model results. So the cyan arrows are the magnetic field perpendicular to the axis, and the orange arrows are the magnetic field on axis. And finally, we have the comparison. So From our experimental values, we get that D equals 0.25455, and B net is equal to negative 1.58 times 10 to the negative fourth, 4.27 times 10 to the negative fifth, 3.42 times 10 to the negative fourth. And then for the model values, we get, again, the same value for D, 0.25455. However, B net, we get a much different value, 8.7 times 10 to the negative sixth, 2.45 times 10 to the negative fifth, 0. So the D's basically perfectly align, which is good. That's what we would expect. However, the values for the magnetic field differ quite significantly. So